Welcome back. We are here with Kevin Mabe, the Chief Analytics Officer of Chorus. It's been a little bit, Kevin, since our last video, but I know that we're really excited about this one. We're going to dive into predictive analytics. Is that right?
Yes, we're definitely going to dive into predictive analytics, what it is and what it is not. So this series is going to be a bit more standards approached and definitions approached instead of necessarily example approach. But I think you'll find it useful.
Awesome. Yeah, and this is we're going to break this out into a couple different parts, so make it a little bit easier to kind of digest and keep the conversation going. Is that correct?
Yes, exactly. So what I'd like to do is start by defining what predictive analytics is, and sometimes that is best done by contrasting it with descriptive analytics. And so predictive analytics, fundamentally means that you can actually predict something or expect to predict something to happen. This is not just a methodological issue. It's also how you even frame up the problem and how you frame up the analysis in the first place in order to achieve what we call predictivity. So as a first step, for instance, we're talking about a holdout sample. Now, this is a very simple graph, but it's actually pretty illustrative. So anytime that you're trying to do some kind of predictive analytics project, you want some kind of holdout sample data. We at Chorus choose at least 35%. There's really no magic for why it is 35 as opposed to 33 or 36. But we want to essentially give the chance that we find these statistically strong signals in the model data, but that may or may not be robust on the holdout data. We actually want to hamstring ourselves to not use all of the data. Some people, when they do holdout samples, they'll hold out 5 or 10% of the sample, which makes no sense to me at all. It is actually very statistically difficult to show non-robustness when you've got a holdout sample that small. And there are applications where if you've got millions and millions of rows where you may hold out half of the data or even 75 or 80% of the data, depending on what you're really trying to do here. But the whole goal of what predictive analytics is twofold. Is one, to split your data into a model data or training set data, however you want to describe it, and a holdout sample that you can then demonstrate that the model fit on these data fits the holdout data in an expected way.
That's great.
So now, what do we mean by the model fitting the holdout data in quote quote the expected way? So this is the second part of what predictivity means at Chorus. So let me give you an example here, and this is actually from a real example of what a non-robust model looked like. So on the blue, just like the blue in the sample here, this is the model fit on the model or training data. So you can imagine that this might be height of a person predicted from factors known at 5 years old. So what's the height of an 18-year-old compared to what do I know about the 5-year-old, etc. So this particular model fit the model data, which was about 65% of the data, 74%. And here's the distribution of the predicted heights. Here's the model fit on the holdout data. So it fit less at about 62%, and it has the shape. So Drew, what do you notice about these two curves?
Well, looks like the standard deviation on the holdout data is a little bit wider.
Correct.
A much narrower channel on the model data that you've got there.
Yep.
But honestly, I don't know what that means.
It's great. This is worth a discussion. So this is what I call a non-robust model, and the reason why is there's three major reasons. One is the R-squares are different. They're not statistically close at all. And so what tends to happen is people will build a model on the model data, fit the model on the holdout data, and then report the fit of the model as the model fit of the holdout data. So in this example, they wouldn't say the model fit at 74%. They would say the model fit at 62% and go on from there. But that's a problem because as you can see, these two numbers are clearly different. And you can even statistically demonstrate that that's the fact. The other two issues are that we've got a difference in means. where the average of the predicted heights is over here for the model data. For here, it's the holdout data, and so those are clearly different. And then, Drew, as you pointed out, the standard deviation is a lot wider for the model fit on the holdout data than it was on the original training data. So there are a bunch of statistical tests that we'll talk through in the third video about, how you can show that these two curves are essentially statistically different. But we at Chorus essentially profess that in order for a model to be predictive, the model has to fit on the holdout data the exact same way as the model training data. And so let me show you from another real-world example about what that looks like. All right, Drew, what do you notice, based on our discussion on the previous slide, what do you notice about what you see here?
Well, obviously there's major overlap. The R-squares are only, 1 percentage point different, which I'm going to guess is not statistically significant. It looks like their means are just about the same, and it's a very tight deviation. It's a long tail, but it's obviously a very tight curve there. So it would appear this is super robust.
Yes.
Whatever it's showing.
Yeah. So you hit all the major heads here. So these two R-squares are in fact statistically insignificant, meaning that there's no real difference between these two. This was a different example, so the underlying distribution has a different shape, but nonetheless, we should expect that the models fit on the holdout data should look like the models fit on the training data, which is the blue. And so you'll notice significant overlap. And again, there are statistical tests to understand the median of these two distributions, the mean, as well as the essential variance here. Now, again, what typically happens is when you're trying to build a robust model such that the model on the training data looks like the model on the holdout data, the performance, what tends to happen is you will build a model that's less predictive, or the R-squared is not as high. However, what you gain in so doing is you're no longer fitting noise, you're actually fitting the strongest signals, and you can be very confident that on your holdout sample that the model fits the same way. And why is this important? Because the whole point of a predictive model is to predict new incoming data. And if you cannot show the internal robustness, even on the data that you have, for instance, in this example, then if I get a new data set, what would I possibly expect as a fit? But in this case, if I got some incoming new data, I would fully expect the model fit the new data in the same exact way. And what's really cool about this is that if that data start looking very different because of different emerging trends or et cetera, the model will be able to tell us where it's not fitting appropriately, but it's the issue with the incoming data rather than the model itself.
That's excellent. That's great.
So that's essentially, that's essentially the difference between descriptive models and predictive models, is how you frame up the problem in the first place with a holdout sample, and then imposing some very strict guidelines and thresholds for saying that the model should fit both the model training data the same way as the holdout data and vice versa.
That's great. So Kevin, we'll pause this one here, and then obviously, as we said, this is going to be part of a 3-part series. So we'll dive in a little bit further in the second and third video, which we'll probably release about a week apart from each other. So as always, my friend, thank you so much, and looking forward to the next one.
Awesome. Thanks again, Drew.